Hi class, this is section 4.1, exponential functions. So let's look at this first example. It says graph both functions on one set of axes. So I would recommend a XY table for these. Actually, I will include, since we're doing this on the same axes, we want to do also the g function. So let's actually call this f of x and g of x. So let's try different values. I would start with -2, -1, 0, 1, 2, just for starters. So if you substitute -2 into x for the f function, you're going to get 5 to the -2, which is positive. That's going to become 25. 5 squared is 25. All right, if you do -1, you're going to get f. Well, actually, let's move on to the g function. So if you do the g function, you're going to get 1/5 to the -2, which means take the reciprocal, and it's going to become 5 to the +2. That's what happens when you raise a base to a negative exponent. You're supposed to take the reciprocal of the base. So the reciprocal of 1/5 is 5, and then the exponent becomes positive. So what do you know? It becomes the same thing. So in general, these are the same. They're trying to get you to see that this is the same thing. And you can verify that by plugging in the rest of these. But in general, a to the -n is equal to 1 over a to the n. So this would be 5 to the -x, which is the same thing as 1 over 5 to the +x, which is exactly the same thing as that. You can rewrite that as 1/5 to the x power. This is the same as that. And so we can just continue to plug these in. And if you do, you're going to get 5 to the -1 is +5. This is the same. Anything to the 0 power is always 1. And if you plug in 1, 5 to the -1 is 1/5, which is 0.2. And then finally, 5 to the -2 is 1 over 5 squared, which is 1 over 25, which is going to be a small number. So 1 divided by 25 is 0.04. Okay, so let's start our graph. Do it down here. Okay, so 1, 2, 1, 2, 1, 2, 3, 4, 5, 6. So when x is -2, you're going to get 25, which is way off the chart. I'll just put a point over here somewhere. So to indicate that this is height 25. And then when x is -1, -1 is here. The value is 5, so 1, 2, 3, 4, 5 right there. When x is 0, y is 1. When x is 1, the value is 0.2. And when x is 2, the value is 0.04, which is way super close to 0. So as you can see, this graph is exponential, and it's decreasing pretty rapidly. And it turns out that this is an asymptote. The graph will never cross it. It'll just get infinitely closer and closer and closer, but never touch it. So that's what the graphs of both of these look like, because they're equal. All right, over here, they want us to graph the function not by plotting points like what we did in the previous problem, but by starting from the graphs below. So the parent function, as they call it, is whatever the base is, which is 5. So the parent function would be y equals 5 to the x, which is this one. Turns out to be this blue line over here, or blue graph. So we're looking at this one here. So based on that, it looks like we want to subtract 3 from the x, which means horizontal shift to the right 3 units. And then this +1 means shift up 1 unit. So let's write that. So we want to the x minus 3 tells you to shift 3 units to the right. And then the plus 1 tells you to shift up, or 1 unit up. And that's it. So we're going to take this blue graph, which is our parent function, and then we're going to do shift it 3 units to the right and shift it 1 unit up. Notice that it goes through 1. All these graphs do. So I'll do my best to graph that. So I'm going to start with that blue function. The blue function looks something like this. That's y equals 5 to the x. And then we're going to perform these two transformations. So if we move this point 3 units to the right, 1, 2, 3, and then we shift it up 1, it's going to be there. So this point goes here. I'll do it in red. And then instead of the horizontal asymptote being at 0, like it is for all of these functions, it's going to be shifted up 1 unit. So the horizontal asymptote will now be at 1 instead of 0. So let's do that in black. And the general shape of the graph stays the same. So now we just have to make sure it goes through that red point. And there it is. So that's it. This point was shifted 3 units to the right, up 1. The horizontal asymptote was at 0, y equals 0. Now it's at y equals 1 because of the vertical shift up. And so that does it for that problem. State the domain and the range of that problem. So the domain, if you notice, it's going to be defined everywhere to the left and also everywhere to the right. There's no point at which it's not defined along the x-axis. So it's all real numbers for the domain. For the range, however, it's only defined, the y values, it's only defined from the the horizontal asymptote up. It's not defined below it. So it's only defined from here up. However, it never touches the horizontal asymptote. Therefore, you need to put an open bracket at 1. Because it never touches it, it just gets infinitely close to 1. So that would be positive 1 to infinity. State the asymptote, well, it's at 1. All right, this next problem is a word problem. If $20,000 is invested at an interest rate of 2% compounded semi-annually, that's the key word. Semi-annually means that n is equal to 2 because that means twice a year. So in general, annually means n equals 1. Semi-annually means n equals 2. Quarterly means n equals 4. What's another one? Monthly, n equals 12. And they might say daily maybe, which we'll just assume is 365 days in a year. All right. So the formula for compounded semi-annually would be, for investments, it's the principal amount times 1 plus r over n, which is the number of times that interest is compounded per year, raised to the n times t power, where t represents the number of years the investment is in there for, and r is the interest rate, n is what we just stated, p is the principal amount that you start off with, and a is the amount that you end up with. So we know that the interest rate is 2%, which is 0.02. We know that n is 2 in this case because it's semi-annually. And it says, find the value of the investment after the given number of years. So t in this case is 4. And the principal amount is $20,000. So let's plug in these values. 20,000, 1 plus 0.02 over 2, and then 2 times 4. The number of years is 4 for the part A. And if you're doing this on your calculator, be careful. You might want to put parentheses here so that your calculator knows that the 4 is in the exponent, not down here. So type this in exactly the way you see it into your calculators, and I'll do the same. And I am getting 21,000. We want to probably round to the nearest cent. Yes, to the nearest cent. I'm getting 21,657 and 13 cents. And the second part will be identical, except instead of 4, t is 8. So all I got to do is change this 4 to an 8, and that's everything. The rest of it stays the same. So I'm going to do that. I'm going to change this 4 to an 8, and I'm going to do the same exact thing. And let's see what that turns out to be. All right, now I'm getting, for that, if I change that 4 to an 8, I'm getting 23,451.57. All right, and that does it for that problem. The last problem says that 1,400 is invested at an interest rate of 4.75% per year. This time it's compounded quarterly, which tells us that n is 4. Our interest rate is 0.0475. If you move that decimal 2 spaces to the left, our principal amount is 1,400 this time. And it says compounded quarterly, so it's basically the same exact formula as before. For this first part is t is 1. For the second part, t is equal to 2. So let's plug these values in to our formula. So for the first part, it's 1,400, 1 plus 0.0475 over 4 to the, 4 times 1. I'm getting 1,467 and 69 cents. And then if I change this t to a 2, that's going to be 4 times 2, which is 8. So let's do that. I'm getting 1538.66. Oops, put the comma in the wrong spot. Should be after the 1, not after the 5. And that concludes this section.